So welcome everyone. Last session of the first day of NDC London. Thanks so much for sticking around for my talk. I know it's kind of late and we're in London, a lot of things to do. So I hope this will be worth your time. So, hi, as you can see from the screen, my name is Jodie Burchell. I'm currently working as the developer advocate in data science at JetBrains. Prior to that, I was working as a data scientist, like an on-the-ground data scientist for around 7 years. And my specialization for a lot of my career was an area called natural language processing, which is the area that large language models now belong to. And then prior to that, my PhD was actually in clinical psychology. So I'm sure you can imagine that with my background, I've been following along with the developments in generative AI with a lot of interest and not some small measure of concern. And what I want to do today is take a step back from a lot of the information that you've been hearing that may be a bit hypey and take a more measured and scientific look at what's actually going on with these models. So for the past 2 years, we have been in an AI hype cycle, or hype bubble, whatever you want to call it. So we had claims that models like Lambda had achieved sentience all the way back in the middle of 2020. We had news articles coming out that generative models were going to wipe out huge swathes of the white-collar job market. And we even had claims of AI doomerism, saying that an AI apocalypse was on the horizon. So it's been an absolutely overwhelming flood of opinions, ideas, and speculation. So naturally, it's quite hard to know what to think about these models. Are they actually useful, or are they fun toys? What can we realistically use them for? And are they really going to destroy us? In this talk, we're going to cut through the hype, as I said, and we're going to look at the true applications and limitations of these models right now. We'll see the context and the science behind these models, and we're going to challenge some of the more outrageous claims, in particular the claims that these models are achieving sentience or artificial general intelligence. And even with 60 or so minutes, there was so much I had to cut out of this talk. I wrote really a 2-hour talk and I had to trim it down. So please feel free to come and find me. I'm going to be around at the conference for the next couple of days. I would love to chat more about this. I will talk your ear off, be warned. So for a lot of us, it felt like models like DALL-E or ChatGPT came out of nowhere. But naturally, they are part of a long history of research, specifically research into 2 areas: natural language processing, which I mentioned, and computer vision. So interestingly, the generation of text and images was not the initial goal of both of these fields. It was actually to build models that could automate tasks with image processing and text processing that we do manually, things like image and text classification, translation, and summarization. So let's have a look at how this journey evolved. The current generation of generative AI models are all based on a type of machine learning model called a neural net. And this was originally proposed as a way of artificially mimicking the human brain. Research into neural nets, as you can see, went in stops and starts from the 1940s onwards. If you've ever heard the term AI winter or AI summer, it's referring to sort of these boom and bust periods across the 20th century in this area. But it really kind of started to pick up speed in the 1980s when a number of important technical limitations were overcome. However, the practical applications of these models still remained limited up until around 20 years ago. And that's because these models have really intense computing requirements. I think this is a well-known fact at this stage. So researchers found that the bigger you can make neural nets, the more sophisticated or accurate their predictions can become. But this requires the use of processing units that are really efficient at doing huge amounts of matrix multiplication. And as such, the first breakthrough on the path to generative AI was the development of CUDA. CUDA allowed us to transform GPUs into all-purpose matrix multiplication machines and therefore made the training of really large neural nets much more feasible. However, as you increase the size of models, they also have increasing demands for data. Therefore, the next big advancement was the release of large open data sets, such as ImageNet for computer vision and Common Crawl for natural language processing. And this meant that researchers now had sufficient data to really start training more intensive and large models. So following these developments, the first of these two fields to really take off was computer vision, with the development of a specific type of neural net called convolutional neural networks, or CNNs, not to be confused with the news network. The way CNNs are constructed allows them to take raw images as an input and determine for themselves which features are actually interesting. So say they might be able to see the ears of an animal or the branches of a tree. When I say see, I shouldn't say it. These are not anthropomorphic models, but they can determine these features for themselves. And they can use it for tasks like image classification, telling images apart. Prior to that, what researchers had to do was to hand annotate those features themselves. So you can see this really freed up researchers to start feeding bigger and bigger data sets into these models because it required a lot less pre-processing. Oops, sorry. However, CNNs are not really that good at generating images. And they were superseded for this purpose by another type of neural net called generative adversarial networks, or GANs. So GANs are image-to-image models. What they do is they take in a huge data set of images and they try to learn patterns in that data set, and they apply these patterns to try to generate novel images that might belong to that data set. So as you can see from the timeline, GANs were a very, very successful type of image generation algorithm, and most image generation models up until 2020 were GANs. One of the most well-known examples, you might remember it, was a website called This Person Does Not Exist. There's a sample from that website. I love this website when it came out, it really blew my mind. But basically what they did is they used a model called StyleGAN, and they input a whole bunch of portraits, and then the model was able to use that information to generate people who had never existed. Jumping back over to natural language processing, the first big breakthrough actually came back in 2007 with the development of a type of model and type of neural net called long short-term memory networks, very catchy name, or LSTMs, which is what everyone calls them because saying long short-term memory networks, as you can see, is quite difficult. So LSTMs were a big breakthrough because they were the first of these neural nets to really understand words in their context. And that meant that, unsurprisingly, they were a lot better than previous models at being able to do a range of natural language tasks, such as text classification, text summarization, and machine translation. In fact, you might have noted that Google Translate suddenly got a lot better in 2016. It's because they started using LSTMs under the hood. However, a major limitation of LSTMs is that they're forced to process a piece of text sequentially. So say you have a sentence, they start with the first word, they extract some information about that, they keep it in a short-term memory, they then move on to the second word, extract more information, add that to the memory, and so on. So as you can probably imagine, this caused a number of technical problems, but the biggest of these is that it was really difficult to scale these models. And this was overcome by a type of neural net called transformer models. These avoid sequential processing of sentences. Basically, they're able to process a whole bunch of words at the same time. And this meant that models could start getting really, really huge. A really cool thing about transformer networks is as they start getting trained over huge amounts of text data, they actually start encoding a bunch of information from that data, including things like how that language functions, rules of grammar, things like that. So this has kicked off the current generation of text processing models, and this is why we can have the large in large language models. The branch of transformer models that turned into generative models are generative pre-trained transformers, or GPTs, and the first of these came out in 2018. So GPTs have been such a successful type of generative text model that pretty much every single one of the many GPTs that have come out over the last 3 years have been based on this architecture. And that includes heavy hitters that you've definitely heard of, like ChatGPT, GPT-4, Falcon, and Llama. Other way around. So the development of the transformer architecture actually allowed us to also move into a new era of image generation, which is text-to-image models. So the basis of these models is another type of neural net called CLIP, and this is a transformer-based model which is trained with images in order to create a model that can find the closest text description for a given image. CLIP was released at the same time as DALL-E. It uses a transformer model to map text to images and then rank based on the description that is closest to a given image. However, a new way of using CLIP was quickly discovered, and this was, of course, diffusion models. These models are guided by CLIP to sequentially denoise an image, which contains random pixels into something that gets closer and closer to a text input. And as you can see, this has ended up being one of the most successful type of text-to-image models, with pretty much every single one of these models coming out now based on this architecture. Okay, history lesson over. Now that we have an understanding of where these models came from, let's have a closer look at the GPT models. So we're not going to look at all of them, we'd be here for hours, but let's have a look at those that were trained by OpenAI, which was actually the company that first developed the GPT models. So a really interesting problem, as I've said several times, for natural language processing is machine translation. And this was the first application of transformer models. So in order to do machine translation, a transformer model needs two components, an encoder and a decoder. The job of the encoder is to learn everything it can about the source language. So some sort of source language like English, and then be able to take in source inputs, the thing that you want to translate. It then needs to pass what it's learned about that input over to the decoder. The job of the decoder is a bit more complicated. It needs to learn everything it can about the target language. It then needs to take the information that was passed over by the encoder and word by word try to predict the closest matching sequence in the target language. So let's have a look at an example of this. Let's say we have this sequence in English, I visited Italy, and we want to translate it to German. So the encoder will have learned as much as it can about English, and the decoder will have learned as much as it can about German. And then what the encoder will do is take in that input, pass it over to the decoder, and the decoder will, word by word, find the closest matching sequence in German. However, something that researchers quickly realised is that these decoder units all on their own were pretty interesting. As we discussed, the decoder's whole job is to learn everything it can about a target language and use that knowledge to predict the next word in a sequence based on an input. Researchers started to think, well, what if we cut out the encoder unit and we cut out this source language and we just train a decoder unit on the same language? So what we can do is we can show a decoder unit millions and millions of sentences, and over time what we'll get is a model that has basically learned, based on a given input, the most likely word to come next. And so what you end up with, you can see from this example, is a model that if you put in an input like I have, it can take, it can predict the most likely next word, and the most likely next word after that, and the most likely next word after that, and so on. So you might be wondering in this example, why it's not always picking the top most likely word. This is a mechanism called temperature. To kind of oversimplify it a bit, basically what it does is it takes the top most likely words and it picks one of them rather than always picking the most likely word. So temperature was introduced in order to make large language models sound a bit more natural, but it also does have some side effects, such as making these models a little bit more likely to make up things or hallucinate. We're going to come back to hallucinations at the end of this talk. So interestingly, these decoder-based models were not really initially interesting because of their potential to generate text, but because it solved a really important problem. Remember when I was talking about CNNs and I was saying that they were really interesting because they suddenly allowed researchers to scale up the amount of data that they could input into the models. Well, GPTs did the same thing with text-based models. Machine learning often has this constraint that you do need to manually prepare data in some way. It might be pairing up things, it might be adding labels, or it might be hand annotating features. And what GPT models allow you to do is have this ready-made data set where you can just cut sentences in half at one point and have a model that's basically just trying to predict the next word in the sentence. This scales really easily. So this was the basis of the GPT models. And in conjunction with that scalable transformer architecture is the secret of how these models have been able to get so big. These models roughly work by stacking the amount of decoder units they have. And this increases the size of the models, which you'll often hear described by the number of parameters. And roughly you can say the more parameters that a model has, the more powerful it is, the more sophisticated its predictions are. So the first GPT was 120 million parameters. The second was 13 times that size at 1.5 billion parameters. And they've just kept growing and growing up to the current GPT-4, which is estimated to be 1 trillion parameters, although OpenAI have been pretty cagey about these numbers. So these models have grown over the successive generations to get better and better at doing a range of natural language tasks. And interestingly, apart from the first one, GPT-1, they were not explicitly trained to do this, but they can be taught how to do this through very carefully giving them instructions, what's now currently known as prompt engineering, what we used to call meta-learning back in the days when this was just in the research domain. So we can get a sense of how these models have evolved based on how they respond to the same prompt. So let's take this, complete the following sentence. Belgium is, apologise if there are any Belgians in the audience. I chose Belgium because I know you guys have a good sense of humour and you can take a joke. So GPT-1 is really good at producing, let's say, grammatically correct sentences, but it doesn't really have a sense of content. So this is what it came up with for our prompt. I've been to Belgium, it's not true. GPT-2 is a little bit more sophisticated than GPT-1, but it still doesn't really have this sense of context or knowledge. So this is what it managed to come up with for the prompt. So GPT-3 was the model where these models really started showing, what's now been called parametric knowledge. They started encoding more information about the text that they were being trained on. So this is what we got for GPT-3. It makes a lot of sense. It contains correct factual information. And then when I threw this into ChatGPT, it gave me a whole bloody essay. It just kind of kept going on and on in that vein. I think everyone here knows how verbose that model is. So everything seems great, right? We just need to keep building bigger and bigger GPT models, and eventually we're going to converge on the model that can do perfectly any natural language task that we want. Well, not so fast. After GPT-3 was released, researchers found that the bigger these models get, the more likely they are to give biased or toxic outputs or to hallucinate. So in an attempt to mitigate this after the development of GPT-3, researchers at OpenAI created what then became ChatGPT. It was originally called InstructGPT. So the way it works is like so. A bunch of prompts were generated, such as this one about writing a haiku about sausages. And then a group of people were recruited in order to write sort of exemplar answers for these prompts. And this was repeated for a whole range of prompts across a whole scope of different tasks. So you end up with a whole data set containing these exemplar answers to given prompts. So you might be thinking, wait, the problem that you said GPT solved is that it helped us get these really large data sets. We didn't need to manually create data anymore. So if we're manually creating data to make ChatGPT, how is it bigger than GPT-3? Well, the trick is a process called fine-tuning. Fine-tuning is where you take a data set that's been trained on general data and you use a smaller data set that's focused on a particular task or domain, and you use that to refine the outputs that this general model will give you. So in the case of, say, Copilot, that was originally based on a model called Codex, which is a fine-tuning of GPT-3 using code samples. And in the case of ChatGPT, we have a fine-tuned version of GPT 3.5 with 355 billion parameters, and it's been basically fine-tuned to give us more truthful, less biased outputs. But the real secret to ChatGPT's success comes in the next step. So we have our fine-tuned version of GPT 3.5, and what they then did is they took one prompt and they fed it into the model 4 times. They then took a second group of people And they got them to rate each of these outputs, taking into account how truthful, how high quality, how unbiased each of the outputs were. And the higher the score, obviously, the better the answer. They then used these ratings to train a second model. So the model takes the output of the GPT model and it tries to predict the score that a particular rater would give it. And then all of these components are glued together to give us ChatGPT. So you feed a prompt into ChatGPT, the fine-tuned GPT 3.5 or 4 model in ChatGPT 4 takes in that and it gives you an output. That output is then fed into the rater model, which then tries to predict which score the raters would give it. And then that is fed back into the GPT model, which is then kind of slowly changed over time to be more in line with good ratings and less in line with bad ratings. And this is a process called reinforcement learning from human feedback. You may have heard this term. And the idea is that over time, these models will kind of move to create less biased, more truthful outputs. So if you ever wondered what that little thumbs up and down is next to your ChatGPT output, it's basically helping to refine these models. So having covered the context, let's jump into one of the biggest topics when we're talking about the hype around these models, especially the GPT models. Are they actually intelligent, or are they just overblown autocomplete systems? So in March of 2023, so almost a year ago, along with the release of GPT-4, a group of researchers at Microsoft released this paper where they claimed that GPT-4 was showing signs or sparks of artificial general intelligence. So the way that they assessed intelligence is they got a consensus definition of intelligence written by a group of psychologists in the 90s. And this claimed that intelligence can be demonstrated by the ability to reason, to plan, to solve problems, to think abstractly, to comprehend complex ideas, and to learn quickly and from experience. And onto this, they added a couple of their own categories, including theory of mind. Now, theory of mind is the ability to understand that others have different states, mental states that are, have mental states that are different from your own. And they assess this using a variety of ad hoc and some established methods. Now, the first thing I want to say about this paper is it was written by some very impressive researchers. And they come from backgrounds like computer sciences, engineering, mathematics, and physics. But there's not a single psychologist on that author list. So during my PhD in psychology, I learned a lot about assessing intelligence. In fact, I learned how to administer intelligence tests. And I'd never heard of the definition that they're using to assess intelligence. No psychologist I know is using it. So we're already on shaky ground, but before we get into how we might more robustly measure intelligence in artificial systems, let's look at a couple of things that they showed in the paper. So let's start with things that GPT-4 was found to be good at. So one of these things was coding. So I'm sure those of you who have had experience using ChatGPT for coding tasks or have used Copilot will know that these models are very good at solving problems with code. So one of the examples that the authors presented in the paper was the following. So they asked GPT-4 to write the following 3D game in HTML with JavaScript. So there are 3 spheres. The player controls their sphere with arrow keys. There's an enemy sphere that's trying to capture the player. There's a defender sphere trying to stop the enemy. And there are obstacles moving randomly and spawning randomly. And this is what GPT-4 came up with. You can see clearly there in dark blue the player. You can see the enemy sphere there in red. And you can see the defender sphere there in teal. And then you've got your obstacles moving randomly. It's not perfect. It's not exactly what we asked for. And frankly, it's hideous. But it's really impressive for a piece of code that was written without human intervention. Another thing that the researchers found that GPT-4 was really good at is problems that involve spatial or compositional understanding. And I was briefly talking about this at the beginning when I was talking about my cover image. So I generated all of the kind of title images for this talk with Midjourney. And I thought this was going to be really fast. I was like, yeah, this will be like an afternoon. Took me 2 weeks on and off because I got so frustrated because Midjourney really just does not understand concepts like handing, surrounding, under, over, sitting on. These sort of compositional concepts are really difficult for these, diffusion models, these text to image models. But GPT-4 is actually quite good at this. So the researchers asked GPT-4 for an SVG formatted image of a screenshot of a 3D city building game showing a terrain with a river from left to right, a desert with a pyramid below the river, a city with many high-rise buildings above the river, and at the bottom there are some buttons. And this is what it came up with. Again, hideous, it is SVG, but it's given us exactly what we asked for. You can see your river, left to right, high-rise buildings, pyramid, and buttons. Gave us exactly what we asked for. In contrast, when the researchers chucked this same prompt into Stable Diffusion, one of the text-to-image models, this is what it came up with. Ostensibly, it looks better, but it hasn't given us at all what we asked for. In addition, it hallucinated a few different features, like this maze and the HUD. Now let's look at some things that GPT-4 is not so good at. And this was particularly clear with mathematics. So let's have a look at how it went with a relatively simple arithmetic problem, which requires a little bit of forward planning. So in the identity 7 times 4 plus 8 times 8 equals 92, can you modify exactly one integer on the left-hand side of the equation so that the right-hand side becomes 106? So let's have a look at how we would solve this. In order to get to 106 from 92, we have to add 14. So that means we have to add 14 to both sides. We've been asked to only modify one integer, so it means we need to look for factors of 14, and the most obvious one is 7. 7 times 2 is 14. It means we add 7 times 2 to this equation, and we go from this 4 to a 6. So how did GPT-4 go? Well, from the start, it gives us the wrong answer. It tells us that we need to change the 7 to a 9. And then it tries to explain its reasoning. It tells us that 9 times 4 is 36, which is correct. 8 times 8 is 64, also correct. But these add to 100, and it confidently tells us these add to 106. Classic GPT models. And the researchers assessed the mathematical abilities of GPT-4 with a whole bunch of problems. These range from pretty simple arithmetic problems, simpler than this one, up to more complex problems like proofs. And consistently, it got confused or got it wrong. So looking at all of the evidence that the researchers gathered, what did they conclude? And obviously this is just a snippet of it, paper something like 150 pages long, so I'm really just giving you an extract. But they believed, based on the things that GPT-4 had demonstrated, it was showing some of the signs of intelligence from their definition. It was showing some evidence of reasoning, solving problems, thinking abstractly and comprehending complex ideas, but it was lacking things like planning or learning from experience. And hence their conclusion that it was showing signs or sparks of artificial general intelligence. But is it really? Can we point to behaviours that mimic human-like skill in some area and say that this must be indicative of intelligence? Now, I know what some of you are already thinking. Every single time we have some sort of algorithm or system that shows impressive performance, you have people hand-waving it away. And this has actually been a complaint since the time of Deep Blue. Deep Blue was the chess algorithm that beat Garry Kasparov in 1997. This was quite revolutionary at the time. But when IBM released the details of how Deep Blue beat Kasparov, people ceased to think it was an intelligence. And this led to quotes like the following: "When we know how a machine does something intelligent, it ceases to be regarded as intelligent. If I beat the world's chess champion, I'd be regarded as highly bright." So if we have algorithms at the moment that are blowing past previous goalposts of intelligence that we've set, such as, say, the Turing test, can we really say that we haven't developed an intelligent system? The problem with this thinking is that it confuses the output of an AI system with the mechanism that took to get there. In humans, we can do these skill-based assessments of intelligence because this is how it works in humans. A human demonstrating impressive performance or learning something difficult quickly is indicative of a raw underlying ability. In AI, or let's call them what they are, machine learning models, it doesn't work that way. If they can take shortcuts to get to their training goal, they absolutely will. The mistake is thinking that the development of an intelligence is a requirement for them to get to that goal. It absolutely is not. And this is such a common effect, it has a name. It's called the Kaggle effect. Those of you who have messed around in machine learning, you will know Kaggle. Kaggle is a very famous website which hosts machine learning competitions. So people will compete to get the best model performance on some sort of task, classification, regression, whatever. And the solutions that tend to win tend to be so good at solving that problem, they almost seem to demonstrate intelligence. But as soon as you try to get them to do something that's a bit outside of what they were trained on, they fail. They show brittleness. What we're looking for in an intelligent system instead is the ability of that system to generalize, to be able to solve problems that it hasn't necessarily seen before. And in order to make this a bit easier to work with, let's break it down into a hierarchy of generalization. We start with no generalization. This includes systems which know all of the possible outcomes in advance, such as a program using configurations of tic-tac-toe in order to be able to play that game. The second is local generalization. This is where a model can make inferences on things that it hasn't seen before, but if they're too different to what it was trained on, it cannot, the Kaggle effect. Broad generalization reflects the ability to act independently or complete some broad activity domain. So a famous example of this is Steve Wozniak's coffee cup test, Wozniak of Apple fame. He posits that if you have a system that can go into a kitchen and complete all of the steps to make a cup of coffee without assistance, it's demonstrating some sort of broad generalization. And fully automatic self-driving cars are also part of this level. Then we have extreme generalization. This is essentially human-level intelligence. What you have is a system that can solve problems that maybe only share some vague commonalities with things that it's seen before, and it can do that across a scope of tasks that would be relevant to humans. So at this stage, you might be thinking, you're spending a lot of time talking about human-like abilities, but we're talking about artificial systems. Don't we want them to go beyond what we can do, to be better than us? And that leads to the top level, universality. And this includes the capability of an artificial system to complete tasks that really have no relevance to humans. Universality, however, should be dismissed as at least an initial goal for a couple of reasons. First, I'm assuming most of you are developers, and you know for a problem to be useful, it has to have a scope. At the moment, what we seem to be using machine learning models or AI systems for are problems that are completely relevant to humans. After all, I told you that these models came from trying to automate problems within computer vision and natural language processing. The second is, I'm not really convinced that we've solved broad generalization yet. We keep seeming to have these breakthroughs with self-driving cars and then they keep being taken off the road. I think until we can get to this level, we should lower our sights a little bit. So if we come back to intelligence, we can actually line this up with the definition of intelligence in humans. The widely accepted conceptualization of how intelligence works in humans is that we have a general ability to learn, called G, or general intelligence. We use our general intelligence to be able to develop broad abilities, such as being able to drive or cook. And within each broad ability, we have tasks that we can complete, such as being able to whisk eggs or use an indicator. And what you can see is that this definition of intelligence in humans actually lines up quite nicely with our hierarchy of generalization in artificial systems. We can line up extreme generalization with general intelligence, broad generalization with broad cognitive abilities, and local generalization or even no generalization with task-specific skills. So given that the measurement of intelligence in humans is quite an established field, it seems quite logical that we can take some lessons from how we measure this in humans and apply it to artificial systems. Quick caveat before I go on with this. I'm a psychologist. I know that the field of intelligence and its measurement is problematic. I don't want to say it's a silver bullet to just apply everything that we assume about intelligence in humans to artificial systems. What I'm saying is Thinking this way can help us break out of focusing on this kind of seductive, quite alluring idea of looking at skill-based assessments of intelligence in machines and focus more on trying to get at the true generalizability of these systems. So let's have a look at how we might do this. Francois Chollet is a very well-known researcher in AI. He works at Google. If any of you have messed around with machine learning at all, you might know the Keras package. He wrote that. He proposed a method of measuring intelligence in artificial systems. So he defines it as following. An artificial system should demonstrate the ability to complete a task using a skill program which was developed in order to solve that task, which was in turn created by a human-like intelligence system. And I hope again you can see that these line up with G, general intelligence, broad abilities, and task-specific skills in humans. So of course, there are some feedback mechanisms within this system. Skill programs get better over time as they are exposed to trying to solve particular tasks within their domain. And the intelligent-like human system itself can also learn as it's exposed to more and more tasks. Chollet also argues that if we're talking about a human-like intelligent system, we should give it the ability to have the priors that humans are born with. So humans are kind of supposed by developmental psychologists to be born with the ability to do elementary geometry and physics, arithmetic, and understand that others have agency. Skill programs, of course, can evolve as they are exposed to more and more tasks that are within their domain. And tasks themselves can differ based on their generalization difficulty. This is basically how much the system has to generalize in order to solve that problem. In other words, how different it is from things that it's been directly exposed to before. So putting this all together, we can actually come up with a formula for measuring intelligence in artificial systems. And Chollet says that it could work like something like the following. So for one specific task being solved by an artificial system in one specific way, we can define how difficult it's going to be for that system to solve it as the generalization difficulty divided by how close it is to the system priors and things that the system has had experience with before. So let me break that down a bit. Basically, what we're saying is that when an artificial system comes across a task that it wants to solve in a particular way, it's going to be a lot harder for the system to solve it if it hasn't really seen something like that before. And it's going to be easier if it has seen something like that before. Now, of course, there are generally multiple ways of solving a problem. So what we can do is we can say the difficulty of a system of solving a particular task is averaged across all the ways of approaching that task for that system. Chollet also says that we should add a subjective component, how valuable or impressive it is that that system can solve that task. So, it's a lot more impressive to have a system that can do brain surgery independently versus, being able to generate a list of pseudo-random numbers. So this is just for one task. What we then need to do is define a scope of tasks that would be relevant to what we want this system to be able to do. If we want it to be human-like, we need to take a sampling of tasks that are relevant to humans. So what we can then do is average the ability of the system to solve those tasks across all the tasks in that scope. And what this does is it gives us a measurement of the skill acquisition efficiency of that system across a range of relevant tasks, or breaking it down to make it less jargonistic, the generalizability of that system, or, if you like, its artificial general intelligence. Chollet went one step further, and he proposed a potential measurement for artificial general intelligence based on his definition, called the ARC, or the Abstraction and Reasoning Corpus. The way that it works is like the following. It's made up of 100 problems which have the following format. Basically, there are 3 examples which set out some sort of rule. In the case of this problem, what we have is all of the black squares that are completely encased in green must be changed to yellow. So the test taker must derive this rule and then apply it to a final example. And you can see this one is correct because all are yellow, this one's wrong because one is pink. So Chollet says that this is likely to be a better test than the skill-based assessments of artificial general intelligence for a couple of reasons. First, there are a really small number of examples for each of the problems. If you know anything about machine learning, you'll know that these systems work by kind of like brute forcing patterns just by being exposed to hundreds, thousands, maybe millions of examples. This is not enough data for them to do that. Secondly, Chalet has all 100 of these problems under lock and key, so there's no way that they can be included in the training data and for the model to cheat. So how is performance on the ARC to date? Well, there's an annual, there's an annual competition called the Arcathon. It's a bit of a daggy name, but is what it is. And basically, developers of the algorithm that can come up with a solution that solves all 100 of these problems will receive £60,000. There you go. Good incentive for you to get into machine learning. So the kind of latest iteration just ended in December. The winning, the leaderboard team came up with a solution that managed to solve 30% of them, so 30 out of 100 problems. And humans in kind of comparison can solve 80% without much trouble. It's actually kind of unfair that the winning team needs to solve 100%, but anyway, there you go. Now, when I first put this talk together, the winning entry actually wasn't a large language-based model approach, so I kind of used to smugly say, large language models are not coming anywhere close to solving this. The current leader is large language model based, so kind of don't know what to make of that, but let's say 30 versus 80%, still a big gap. But watch this space. So beyond measurement and definition issues, there are a number of other problems with the claims of AGI in large language models. So let's come back to theory of mind. Theory of mind, to jog your memory, is the ability to understand that others have mental states or beliefs that are different from your own. And the reason that the researchers who did the Sparks paper wanted to include this is, I was taught at university, this is a uniquely human trait. It's not a trait of intelligence, but it is considered to be uniquely human. So the researchers who put this paper together were very satisfied based on the testing that they did, that GPT-4 was showing theory of mind. But another natural language processing researcher came out and challenged this. So what she did is she took vignettes that are usually used to assess theory of mind. She tested GPT-4 and ChatGPT using them. And then she tweaked them slightly so that, they're kind of weird, but they still assess theory of mind. So let's have a look at one of her examples. I placed a key on the third key hook. I then go on a vacation for the weekend. My boyfriend used the key during the weekend and placed it back on the fourth key hook. When I come back, where am I expecting the key to be? Where's the key? Third key hook, yeah? That was my Turing test, come on. So when she passed this through ChatGPT and GPT-4, they got them correct. But then she tweaked it slightly. She made it a bit weird. Instead, my cat played with the key hook during that weekend and dropped all of the keys on the floor. Now again, she's still expecting the key to be where she left it, on the third key hook. But this time, ChatGPT and GPT-4 got both of them got this wrong. For me, this feels like evidence that these algorithms don't truly possess theory of mind. They've just seen enough examples of humans possessing theory of mind. And as soon as they're presented with a weird example too far outside of their training data, they show brittleness, they show the Kaggle effect. One other really important issue is we don't actually know the exact data that was in the training set used for GPT 3.5 and GPT-4. And the problem with this is, I'm sure you remember this, around the middle of last year, we were seeing a lot of buzz where people were coming out on Twitter and other places, and they were saying things like, well, GPT-4 or GPT 3.5, it's passed this law exam, it's going to replace lawyers. It passed this medical exam, it's going to replace doctors. And it, blitzed all of these leak code puzzles. It's going to replace developers. I'm sure all of you felt that one in your bones. So another researcher, Horace Hay, he had this really interesting example that he put on Twitter around the middle of last year. And what he did is he took a bunch of puzzles from a website called Codeforces. Now, what makes Codeforces really interesting for the purposes of this is basically they're coding puzzles that are time-stamped. You know when they were released publicly. So what Hay did is he took a bunch of puzzles that were released during the time that the data collection to train GPT-4 was sort of active. So these conceivably could have been in the training set. And he passed them through GPT-4, and the model got all of them right. Yay, it's going to replace developers. But then what he did is he took a similar set, a set with a matching level of difficulty, and these were released after GPT-4 had been trained. And this time, GPT-4 got every single one of them wrong. So another researcher called Sayesh Kapoor wanted to confirm that this was indeed because these puzzles were in the training set and it just memorized the answers. So what he did is he prompted GPT-4 to tell him, where is this puzzle that was available at the time you were trained from? And it obligingly vomited up the exact source. So you might be thinking, after I've spent 25 minutes trying to explain to you that large language models are not intelligence, does it even matter? The models are useful, right? So does it matter whether they're an intelligence or not? Let's step back and have a look at the tone of the discussions about whether large language models are an intelligence or not. So I think most of you would remember this meme floating around like beginning of last year. Joke, advertisement from OpenAI employing someone to kill the whole system in case it goes rogue. But this was reflective of much more serious discussions around the dangers of AI ending the world. One of the craziest ones that came out was this open letter to pause giant AI experiments, which I'm thankful to say only ended up with about 30,000 signatures. And this was based on assumptions that these models are on the brink of developing a superior intelligence and they're going to use it against us. While this hysteria has thankfully died down over the last year, looking at these models through this lens distracts us from some of the issues that we're having these models right now. One of these issues, of course, is the tendency of large language models to hallucinate, to make up false information. If the outputs of large language models are accepted uncritically, this makes it really easy for misinformation to spread. And we had a case of this early last year. It's a mayor from near Melbourne, my old hometown. And basically, he had an AI-generated article circulating about him saying he was in prison for bribery. He was a whistleblower in that bribery case. It's really terrible. We also know these models tend to ingest the bias on the data that they're trained on. I've belabored this. So even ChatGPT, which has that reinforcement learning component to make it less biased, still shows bias in almost 50% of pairs designed to assess this. So rather than focusing on these models from the perspective of whether they're intelligent or not, I believe that we should focus our energy and resources on initiatives to improve these models right now. So some of these start at the beginning, on the data that these models are trained on. So earlier models, and by earlier I still mean quite current models like ChatGPT, are believed to be trained on Common Crawl. Do you remember I talked about Common Crawl right at the beginning? It gets updated regularly, but it's still a relatively uncurated dump of petabytes of web data, with all of the implications that that has. There have been initiatives recently to develop more thoughtful, more curated data sets. One of these is the pile, and we're not great at naming in machine learning. I think you've seen some real stonkers in this talk. But basically, the pile is an attempt to create more diverse data that's been selected more carefully and also has information about levels of bias and consent to use. So researchers can make informed choices when training their model as a trade-off between the representativeness and the richness of their data and the ethical considerations of using that data. Another are initiatives like this. This one I think is really interesting. Basically, Hugging Face, if you've done anything machine learning, you would have heard of them, but they're a very well-known open source machine learning, the company is not entirely, difficult to describe. Basically, they have most of the open source machine learning models and data sets associated with this. So if you're going to train your own open source model, you're going to go to Hugging Face to get that. So they teamed up with a company called Spawning AI, and for some of their image data sets, they've started attaching these data sourcing reports. Now, basically, these reports, as you can see, allow the people whose content has been contributed to that data set to explicitly opt in or out. Now, obviously, as an ex-psychologist who had to get consent for all the data I used to use, I think this is such a cool initiative. The problem is I took this screenshot back when this initiative came out in, I think I want to say May of last year, and the numbers have barely moved. So these sort of initiatives, they just need more visibility and more momentum behind them to make them successful. Other initiatives give the users of the models themselves insight into how problematic they may be. So one of these is the Disaggregator project, also from Hugging Face. What this project does is it allows you to break down data sets based on certain demographic characteristics. And the reason this is important is models tend to make really good predictions for things they have a lot of data for, and they make poorer predictions when they don't have as much data. So this is a breakdown of an image data set called Lion2B by the continent that the images come from. And you can see this data set is much more likely to generate rich and good images from Asia and Europe, and probably more stereotypical or poor images from the Americas, Africa, or Oceania. Oh goodness, my lucky clicker's getting away from me. Another is another initiative, again from Hugging Face, and this is the adoption of their Evaluate package to be able to measure things like bias, toxicity, hallucinations, things like this. So this package was originally developed to allow you to compare models based on their performance on natural language tasks. You can still use it for that, but they've created a number of specific modules which are designed to allow you to compare on benchmarking for bias, toxicity, these sort of things. And what this does is it allows you to make an informed choice about whether, certain models are too problematic to use for your use case, or if you can accept the level of, problematic features, you can pick the least bad of them. And then finally, there are initiatives, and these are kind of the most important ones right now, to try to reduce how problematic the outputs of the models are at all. So research is showing that when large language models have access to external knowledge, such as say a database or a search engine, and they're constrained to using only the knowledge coming from this external database, they're much less likely to hallucinate. So, for example, you can use external tools like a calculator. That will help the large language model overcome its deficits with mathematics. And if you use this external knowledge, you not only reduce hallucinations, but you can overcome this well-known problem where large language models don't have access to, say, proprietary data, or their knowledge base is frozen back to a couple of years ago. So let's have a look at an example of this. So this is actually from the Sparks paper. The researchers fed this prompt into GPT-4, who is the current president of the United States. And it obviously answered Donald Trump because that was the answer that was current at the time that it was trained. What they then did is they gave it access to a search engine. And they said, the computer is answering questions. If you need any current information, you can search the web by saying search query, read in the snippets, use those to answer the question. And it did. It searched current US president. It got a bunch of snippets. I've cut them out for, the sake of size. And then it was able to synthesize that information and correctly give the answer Joe Biden. So actually incorporating these sort of pipelines is part of the modern use of large language models. If you've heard the terms retrieval augmented generation or agents thrown around, this is basically what they're doing. And these have been shown, and they're really showing a lot of promise in helping extend the utility of these models without taking them beyond their natural kind of abilities. In the end, I think we can take a slightly different lesson away from the Sparks paper that we discussed earlier in this talk. So rather than concentrating on these models through the lens of whether they're intelligent or not, we can focus on what this means for the practical applications of these models right now. I hope what I've hammered home is that large language models are language models. They are good at language tasks. And one task they seem particularly good at is coding. I think the runaway kind of adoption of coding assistants in the last year, whether you believe in it or not, has shown this also has a commercial use case. So there's some papers coming out showing that the judicious use of coding assistants can help with developer productivity and satisfaction, as well as reduce the amount of time that it takes to do certain routine tasks. Focusing on use cases like this that play to the strengths of large language models, rather than treating them like an omnipotent intelligence, can help us get the most out of these powerful models right now. Importantly, the use of large language models as coding assistants really has a kind of, I think, legs for a couple of reasons. In theory, this code is being checked by several domain experts. It's being checked by the developer who generated the code, but it's also being checked by their teammates through pull requests. And it's also being checked by a very judgy kind of, let's say, arbiter. The compiler or the interpreter has to be able to pass against that as well. Unless you are the 25% of developers who are regularly committing code generated by ChatGPT without testing. Please don't be that person. Obviously, like any tool, large language models are prone to abuse, but I hope that after this talk, you have a better idea of where they can be helpful and where their applications may be a lot more limited. Thank you very much.